Well, thank you for the introduction. It's really a pleasure to be here. I am the director of the Australian Research Council Centre of Excellence in Quantum Biotechnology. It's a real pleasure. It's a particular delight to be here with the topic of today being life and planet, because when we, as the sort of collective chief investigators in QUBIC, started thinking about what QUBIC would be, the priority was to try to build a quantum center that can make a difference to life and the planet. So that's great. I'm also the interim director of the Queensland Quantum Decarbonisation Alliance, which is an initiative which was funded as part of the Queensland Quantum Advanced Technologies strategy. And my job today is to tell you a little bit about how that's going. And I need to start with a little gloom and doom. Last year was the hottest year on record. This trajectory is likely to continue. It's predicted to lead to more extreme weather. Now, I felt like it was a bit prophetic, the weather that we've had in the last couple of days. I wouldn't want to attribute it to climate change, but we can certainly expect extreme storms and fires to be more common. I can't remember biking home and being able to look directly at the sun because of smoke for some years, and that was quite an experience yesterday. But on a serious note, we can expect there are billions of people in the world who are vulnerable to changes in climate. And there's a major economic cost too. So the predicted economic cost is in the range of trillions of dollars globally per annum. And so we need to be thinking about this as both a major risk, but also an opportunity. If there's trillions of dollars of risk, then as a globe, we should be investing a lot of money to try to deal with this risk and mitigate it. And what's important to realize is that we don't have the solutions we need to get to net zero by 2050 yet. We need new technologies, and we need them fairly quickly. The argument that the Queensland Quantum Decarbonisation Alliance made to the state government was that quantum has a meaningful role to play in this, and that we in Queensland and Australia can lead the world in deploying quantum technologies towards net zero. Okay, so how can quantum technologies help? Well, as you heard in David's great keynote talk this morning, there are three primary types of quantum technology: computing, communications, and sensing. Our belief in the QDA is that computing and sensing are likely to play the biggest roles in helping us decarbonize. Computing, if you think about decarbonisation, there are many extremely hard computational problems that are involved, which are beyond the scope of current computers. So that opens the natural question: well, can quantum computers help address some of these problems? In some cases, I think it's fairly clear that should useful quantum computers be built, that they will, particularly around chemistry. So if you think about designing batteries, then it's all about chemistry. How do you get higher densities? How do you make them more robust? How do you make them last longer? And similarly for carbon sequestration, how do I design membranes that can best extract carbon out of the air? And catalysis, how do I create ammonia for fertilizer more efficiently? And then there are a whole set of applications and optimization. You heard in the last panel about optimization for transport for the Olympics, but of course, if you can improve transportation times, you're also reducing pollution. There's a report that I think has been quite influential on quantum computing for decarbonisation by McKinsey a few years ago now, and they identified many potential applications and make the claim that quantum computing could help us reduce carbon emissions by about 7 gigatons a year. Now that's a big claim. There are a lot of ifs, biggest one being when will we get useful quantum computers? But that represents about 17% of what we need to remove to reach net zero. So it's a significant fraction. In quantum sensing, we will need a great deal more critical minerals, as I guess you've seen from the news in the last few weeks, than we currently even know exist if we wish to make the transition to net zero with existing battery technologies and other technologies. So we need to have good ways to find minerals. We need to have better ways to efficiently extract them. And quantum sensors can play a role there. David's presentation had the CSIRO LANTEM magnetic sensor, which has been used to find billions of dollars of iron ore. So there's an example already out there. And quantum sensors can do more than that, particularly quantum gravimeters and quantum magnetometers. Gravimeters can tell you about the density of stuff, and that means you can understand how much water there is in aquifers. You can monitor whether carbon is leaking out of carbon sinks deep under the earth. And similarly, other sorts of quantum sensors can tell you about methane and carbon dioxide emissions from industry and mine sites. So there are many places that quantum sensors can play a role. This is the LANTEM sensor that David already showed you as an example of a portable magnetometer. This is an example of a portable gravimeter that you can buy now that's commercially available. So the question then is, if we accept that there are potential applications of quantum in decarbonisation, how do we go about going from that concept to reality? And the belief is that in order to do that, you need, just like in the quantum for the Olympics panel, we need the right set of stakeholders and partners. It's not enough for people like me in a quantum lab to develop a technology. We need the right pull factors telling us what problems do you actually need to solve, and where is the value and how do you make it happen, and then working with us to deploy the technologies in those applications. So the QDA is designed in precisely that way. Its mission is to apply quantum technologies towards reaching net zero, partnering with industry to identify, develop, and roll out high-value use cases. We have 4 key partners: the University of Queensland, Griffith University, CSIRO, and PsiQuantum. And we have about 27 partners from across industry, academia, and government, supported by a $30 million investment, $10 million from the state government, and $20 million in cash and in kind from all of our other partners. I want to emphasize that the aim is to do research, but go beyond research. So we want to partner with industry and spin outs to drive real world impact. One example is with PsiQuantum. Most people here, I guess, will be aware that PsiQuantum are building a utility scale quantum computer here in Brisbane. You may not be aware that they're also establishing a climate research centre here in Brisbane, which will have quantum algorithm specialists specifically focused on designing solutions for quantum computers in the decarbonisation space. Another example of impact in terms of commercialisation is a company which has recently spun out of my lab called Asonic, founded by Glenn Harris, who's in the audience, who still is in the audience here, and you'll see on a couple of panels later on today, and Chris Baker. This work, of course, predated the Queensland Quantum Decarbonisation Alliance. It's work that we were doing in the lab for over a decade with Lockheed Martin to understand how you could use phonons, or vibrations of sound, acoustic waves on a chip, to do computation. And this then Cortisonics mission is to revolutionize AI with reservoir computing. And the big benefit of using acoustic waves is that they have many orders of magnitude lower energy than electrons and photons. So you can address the energy consumption of AI with these techniques. Yes, okay. I wanted to finish by giving you 3 examples of research innovation, or tell you about the 3 research innovation themes of the QDA, and give you 3 examples of areas that we want to work in and are working in. I would say that we are in the process of hiring 7 new faculty across Griffith and UQ, who will be the engine of the Alliance, at least from a research point of view. I hope that we'll have some exciting announcements about those positions in the next few months, but I can't say anything about it quite yet. So the 3 research areas are green hydrogen and agriculture, electricity and batteries, and resources and carbon sequestration. In the first of those areas, agriculture, a very prominent example is fertilizer production. We currently make fertilizer with a process that was invented about 100 years ago by Haber and Bosch. That process requires very high temperatures and very high pressures, so much so that to feed the world, we use somewhere between 1% and 3% of world energy just to produce fertilizer, and 4% of world methane. If we stopped doing this, in fact, there's an experiment that has been done. Sri Lanka stopped doing this. If you stopped using artificial fertilizers a few years ago, and their government was overthrown. So we need to produce this stuff, but we need to do it in a way that's more environmentally sustainable. And what is interesting is that plants do it all the time. Leguminous plants, they have these. I'm not a plant expert, and my pointer doesn't work, but these lumps on the roots are, maybe they're called legumes. That's possible. Maybe not. They are. But inside them there are bacteria, and inside the bacteria there's an enzyme called nitrogenase that happily produces ammonia, which is the core chemical in fertilizers, at room temperature atmospheric pressure. Quantum computers could help us understand these enzymes because the reaction site is too complex for regular computers to simulate. And if we can understand it, then the hope is that we can learn from it and design artificial catalysts that do the same job and allow us to produce fertilizer at much lower energy cost. Second example is battery technologies. Batteries will, as long as we can make enough of them, deliver about 20% of the carbon abatement we need to reach net zero. But battery, and you will have seen a rapid advancement in battery energy densities and robustness in the length, the distance you can drive on a battery. But battery chemistries are complicated. Here I'm showing you an example of a simulation of how the cathodes, the anodes in a battery degrade over time depending on the chemistry of the anode. These sorts of simulations are hard to do, they're approximate, and they're computationally intensive. So the hope is quantum computing can help us do better simulations and therefore design batteries that are not only have higher energy density, but are more robust and cheaper to make. And it turns out that there are already about 1,000 publications per year on the applications of quantum computing in battery technologies. So we're excited to work in that space. And the final example is critical minerals. I think I mentioned earlier that we don't have enough mineral supply to fuel the clean energy transition as of today. This is true, and there are many, many minerals that are needed for the different clean energy technologies. it turns out that we're likely to need about 40 times as much lithium per year as we can currently mine, and we're likely to need about 20 times as much cobalt and 20 times as much nickel as we can currently mine. We don't even have known reserves of cobalt, which are going to provide that much cobalt by 2040. That's by 2040, not even net zero at 2050. So the world desperately needs more minerals. And I guess the good news story for Australia and Queensland is that we have a lot of minerals. So there's a real opportunity. There's a major global risk, but there's also an opportunity for Australia. For example, where we have the second largest cobalt deposits, and we have the second largest lithium deposits, and we have the most nickel, zircon, and rutile titanium in the world. This is something that the Queensland government has recognised. There's a Queensland critical minerals strategy. This is a map of all of the critical minerals that have been identified in Queensland. But there's a real opportunity to find more such minerals, and I think quantum sensors will play a major role in that. And I wanted to give you two examples. So the first example is Nomad Atomics, which is, I'm going to get this wrong, I think they're a Canberra-based company, but maybe they moved to Melbourne. They came from Canberra and moved to Melbourne, thank you, David, who develop portable atomic gravimeters and have a roadmap from their present devices, which you can see up the top here, all the way to devices that you can deploy on a drone and in vehicles. And the second example is from my lab in collaboration with Defence, Orica, Griffith University, and others. And this is a magnetometer, precision magnetometer that we can deploy on drones now. Has performance close to the best cryogenic magnetometers, although not quite there yet, but I think we will get there. And one particular application with Orica is to do smart mining, to better know where to drill and how to, where the valuable minerals are. So with that, I think I'll finish. I'm not sure if there's time for questions or what the plan for questions is. Am I over time? I'm about on time, so maybe one burning question.
Do we have a burning question out there?
No burning questions. Okay.
I'll ask a burning question. Are there any of the critical minerals, for example, if you guys need to set up computers, are there any critical minerals that currently don't get used in great supply, but you can see ramping up? Like obviously there are quite a list up there, and some that a lot of people have heard of, cobalt's, coltan. There's a lot that we know of that we'll need, but some of the rare scandium or elements like that we sort of think, oh, that could actually ramp up depending on what quantum finds as the best catalyst or the best battery.
Are you saying, okay, you're saying, are there rare earths that are underutilized right now?
Yeah, basically.
But
that's a better way to put it.
Could be used. Well, actually, I don't know. I guess there are elements that we don't use very much in industry, but probably it's a very difficult question for me to answer because it's actually a perfect example of the kind of issue that we have in areas like quantum decarbonisation. I'm a quantum expert. I know a fraction of the story. If you ask the same question to someone in mining, they know part of the story, but they also couldn't answer the question because they don't know the quantum part of it. So we need to bring the environment, these different parties together and then hopefully answer the question. And that is in fact exactly what Chris's presentation is about.
Excellent. That sounds like a perfect segue. Can we start please by thanking Warwick? Thank you very much, Warwick.